Okay, this is lesson 13.1, Measures of Central Tendency. When working with numerical data, it's often helpful to use one or more numbers to describe the whole data set. Measures of central tendency describe the center of the data. So these three measures, these three statistics, are different ways to represent something that is typical about the data set or the center of the data. And in a few minutes, we'll talk about when you might use one over the other. So the first one is the mean. This is just the average. That's all that is. That's the sum of the data divided by the number of items in the data set. So for example, if you had 5 numbers, you'd add up the 5 numbers and then you'd divide by 5. If you had 18 numbers, you would add up the numbers and you would divide by 18. So it's just the sum of the numbers divided by how many numbers are in the set. The second one is the median. That is the middle number of the ordered data. So you would put the numbers in order and you'd find the one that's in the middle. Now if there's two numbers that are in the middle, then you would just take the mean or the average of those two numbers. And you will see this in a couple sets of data in this video. And then the last one is just the mode. That's the number or numbers that occur most often. So it's just the most common one. Okay, so let's look at the first example. It says Jason recorded the number of hours he spent watching television each day for a week. Find the mean, median, and mode for the number of hours. Okay, so let's start by finding the mean. Well, the mean is just the average, and we have 1, 2, 3, 4, 5, 6, 7 numbers. So we will just add those 7 numbers together and then divide by 7. So we have 2 plus 3.5 plus 3 plus 0 plus 2.5 plus 6 plus 4, all divided by 7. So let's go ahead and add these together. And you should get 21. So then 21 divided by 7 is 3. So the mean or the average of this set of numbers is 3. And since this represents hours spent watching television, this would be 3 hours. Alright, in order to find the median, we need the numbers to be in order from smallest to biggest. So let's go ahead and start listing these. So we have 0, 2, 2.5, 3, 3.5, 4, and 6. And I always, when I put these in order, I always like to count them to make sure that I've included the right number of numbers. So we should have 7. We have 1, 2, 3, 4, 5, 6, 7. Okay, so now our numbers are in order. Well, we want the middle number. So if you have a lot of numbers, sometimes it's helpful to actually count how many you have and figure out where the middle would be that way. But when you have a small set of numbers like we have here, it might be easier to just think about canceling out one at each end at a time. So like 0 and 6, and then 2 and 4, 2.5 and 3.5. And then here we are in the middle. This is the median. So the median is also, just like the mean was 3 hours, the median in this set is also 3 hours. This tells you that half of the numbers are greater than 3 and half of the numbers are less than 3. It truly is the middle number. Okay, and the last thing we need is the mode. Well, we just want to look through, and in this case it actually is helpful to have these listed in order because then anything that's the same will be grouped together. But if we look through this list of numbers, you'll see that there's no number that appears more than once. So, and this is possible in a set of data. In this case, there's no mode because none of the numbers appear more frequently than any other numbers. Every number appears only once. Okay, so for the two try it yourself problems, you're going to do the same thing. You want to find the mean, median, and mode for each of those sets of data. So pause the video and find those 3 measures of central tendency, and when you're ready to check your answers, press play. Okay, so for the first one, Maria's test scores, you should have gotten a mean of 84.625. You should have gotten a median of 90, and then a mode of also 90. For the rainfall last week in inches, the mean rainfall was 0.16, the median was 0.1, and the mode is 0. Okay, so you'll see from these sets of data and from the one that we did already, sometimes the numbers will be the same, like here the median and the mode are the same. In this first set of data, the mean and the median were both the same. And sometimes all the numbers are different, like here. And you can see here, these may seem like they're very close, but when you look at the kinds of numbers we're dealing with, these actually aren't really all that close. So sometimes it's important to think about which measure of central tendency best represents the data. Because, for example, um, if you're trying to give information to somebody without giving them the entire list of numbers, sometimes one um, measure of central tendency makes more sense or is more appropriate in that situation than another. So let's take a look at the table at the top of the next page. It says different circumstances determine which measures of central tendency are most appropriate. So this is when you might want to use each of these. The mean, first of all, is most useful when the data have no extreme values, values that are much greater or much less than the rest of the data. Extreme values highly affect the mean because the mean is sensitive to every single value in the data set. Um, so think about this in terms of like your grade in a class. Um, your grade is basically an average. Yes, it's a weighted average, but it is basically an average. So that's why when you have an extreme value, it can make a huge impact on that. So for example, let's say you've had several decent grades, A's and B's, and then all of a sudden you get a 0 on an assignment. Well, you'll notice that, especially if you look just at that single average, like a homework category or something like that, you'll notice that that will make a huge impact on that average because the mean is very sensitive to a single grade. Um, Now, if your grades are close to that average, it doesn't really impact it that much. But when you have these extreme values in an average, like I said, like a really low grade, it can really impact the mean. So we wouldn't want to use the mean to represent data if there are extreme values because the mean will be a little bit skewed if that's the case. The median you would use when the data have extreme values because think about, for example, if we go back to this list of test scores, notice here the difference between the mean and the median because of this really, really low test score here, this 50. Well, if you look at the median, her middle score is still a 90. So half of her test scores are above 90 and half are below. But the median doesn't tell you how far below. So this 50 and even this 74 is kind of low also. Those extremes didn't really affect the median at all. But the mean, notice how far that's pulled down based on that 50 and a little bit from the 74 as well. So the median is very useful when the data has extreme values because it'll still give you the middle. But you want to make sure you're not using the median when there are big gaps in the middle of the data because then that median won't really represent the data very well. So you want data that's kind of all around the same area, and extreme values would be okay, but no gaps in the middle. The mode is useful when the data has many repeated numbers. So if it's a lot of the same numbers, mode would be helpful because the mean and the median, if the numbers are really close together and there's lots of the same number, the mean and the median won't represent that as well. Whereas the mode, with a lot of the same numbers, you'll be able to look at which one's most common. So these are just some general guidelines for when one might be more appropriate to use than the other. Extreme values in a set of data are also called outliers. That's the term that we'll use to represent those because they lie outside the overall pattern of distribution. So these are values that are extreme, very high or very low compared to the rest of the data. And we'll actually have a definition in the next section for what determines if something is an outlier or not. So let's look at example 2. It says the monthly grocery bill of 3 families was collected over 6 months. Which measure of central tendency best represents the data for each family? Okay, so let's look at the data we have. So let's look at the Pine family. So in this data set, I'd say first of all that there is no mode. There's not a single number that's repeated more than once. So the mode definitely is not the best measure of central tendency to represent this. And if you look through here, we have numbers that are in the 300s and we have numbers that are in the mid 100s. So this would be an example of where the median would not be useful because there are big gaps in the middle of the data. We have a cluster in the 100s and a cluster in the 300s. So the median here would be very sensitive to just how many in each area we have. So in this case, we have 3 that are around the same area and 3 others that are around the same area. So the median is not going to be the best representative here. And since there is no mode, we're left with the mean. And it does fit that. The data has no extreme values. Notice they're all, they're in 2 clusters, but they're all clustered around each other. So there's no extreme values. The mean here would be the most appropriate. So for the Pine family, the mean would best represent theirs because of gaps in the data and no extreme values. Okay, let's look at the Kim family. So their data is very close together, ranges from 193 to 254. But we notice there's 1, 2, 3 months where their grocery bill was $210. So we do have a mode here. Um, and there are no gaps in the data really. Um, there are no outliers. But in this case, because we're talking about the monthly grocery bill, if they're spending $210, which also is pretty representative of the data. There's one that's less than that, one that's a little very, very close to it, but a little bit higher, and then one that is a bit higher than that. But 210 is pretty well in the middle, and it's pretty representative of this data. So this would be a good case where you might want to use the mode to represent it because that number shows up multiple times. So that would tell you what a typical grocery bill would be for the Kim family. So for the Kim family, we will use the mode because we have repeated numbers. Okay, and then the last one, the Diaz family. So if you look through this list of numbers, you might see something that's a little out of the ordinary. 204, 187, 195, 214. What on earth happened here? So you can see how this is definitely an outlier. It's an extreme value because it's so far away from any of the other ones. So in this case, when we have extreme values, we can't use the median or the mean because the mean is sensitive to those extreme values. The median would be most appropriate. So we don't have any gaps in the middle of the data. That ranged from like 146 up to 214 where most of the data is located. No gaps, so the median here is perfectly fine. So for the Diaz family, we would use the median because of the outlier. Okay, so using that same reasoning, you want to look at the try it yourself problem and determine what measure of central tendency best represents this data. So go ahead and pause the video, answer that question, and when you're ready to check your answer, press play. So for this one, if you look at the way the data is distributed, all the numbers range from 0 to 4. And there's multiple instances of every single number. There's a couple zeros, there's a couple ones, there's a couple fours, a couple threes, and a whole bunch of twos. So in this case, the mode would have been the most appropriate one because you have multiple repeated numbers. And also just because the numbers are close together, so the mode isn't going to misrepresent the data. For example, if you had, a small handful of low numbers where they weren't really repeated, and then a cluster of, two or three um, really high numbers where the mode would be misrepresenting the data, then the mode wouldn't be appropriate. But in this case, the twos are right in the middle of the data set. It's actually just about perfect. So the mode here would make the most sense. Okay, so that's section 13.1. We're going to skip 13.2 and come back to it when we'll look at it along with 13.4 and 5. But we're going to go to section 13.3, measures of variation. Measures of variation are used to describe the distribution of the data. So in the first section, we had measures of central tendency that showed you where the center of the data was, whether that was measured by the average or the middle or the most common number. We were looking for the center of the data. Measures of variation tells you how much variation there is. So how big of a difference is there between the biggest and the smallest number? How spread out are the numbers? So these are each terms that we'll use to describe the variation. So you have the range, which is one of the things I mentioned, the difference between the greatest and the least values of the set. So for example, that last try it yourself problem had a very, very small range. Even though there were a lot of numbers here, they only ranged from 0 to 4. So that would have a range of 4, very small. Whereas, for example, the grocery bill for the Diaz family had a large range. The lowest value was 146 and the highest was 416. So the range here was over $200, over 250 actually. So that's a big difference. So you can see how the range there tells you something about how distributed the data is. The median we've seen already, but we've seen a slightly different definition of median. The median is the middle number in a set of data, and I've hinted at this already. It's the value that separates the data set in half. So wherever the median is, half of the numbers are above that number, and half of the numbers are below. The lower and upper quartiles will take, when you have the median that splits the data in half, the lower quartile and upper quartile separate each of those halves in half again, and that's why it's a quartile. So think quarter, like fourths. So the lower quartile is the median of the lower half of the set of data. The upper quartile is the median of the upper half of the set of data. So once you've found the upper and lower quartiles, you can find the interquartile range, which is just the difference between those two things. And these will all make more sense once we look at an example. So if the word quartile is starting to sound like nonsense, it'll make sense in a minute. And the last thing, we talked about this in the last section also, an outlier, but now we actually have a solid definition for what constitutes an outlier. Data that are more than 1.5 times, this number is important, 1.5 times the value of the interquartile range beyond the quartiles. So for example, if the interquartile range was 7, then any data that's more than 7 above or below those quartiles would be an outlier. Okay. All right, so let's take a look at example 1. We want to find the range, interquartile range, and any outliers for the set of data. Okay, so to find the range, we would need the numbers, we would need to find the smallest and biggest number. And because we're going to find the interquartile range, which means we'll need the median and the lower and upper quartile, let's go ahead and just start by listing these numbers in order. So the smallest one is 2.5, And then we have a couple of 3s and a 4.5. Got a couple 5s and a 6, 8, and 14. Okay, so we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have an odd number, so our median will actually be the middle number. So 4 on each side. The one in the middle is right here. That's the median. Okay. Now, when you go to find the upper and lower quartile, if the median is part of the data set, now the lower half is just these 4 numbers and the upper half is just these 4 numbers. The 5 is the actual median, so it doesn't count in the upper or lower half. So in here we have 4 numbers, so the middle of those 4 numbers is right between these two. Now if these were different I would average them, but the average of 3 and 3 is still going to be 3. So this is the lower quartile, which is 3. In the upper half, we have 5, 6, 8, and 14. And again, 4 numbers, so halfway between would be right in the middle here. And right between 6 and 8, you can probably tell me that that is 7. But if that wasn't super obvious, we'd add those together. 6 plus 8 is 14, and then divide by 2 to get 7. So there's our upper quartile, is 7. So notice now that we have 4 equally sized sets of numbers. We have 2 numbers here, 2 numbers here, 2 numbers here, and 2 numbers there. Now when I say equally sized, I simply mean that there's 2 numbers in each set. Clearly they're not the same distance apart. These are very close together, these are very close together, these are close, these are not. But we have 2 sets of numbers in each group. We've split the data into 4 equal parts. Okay, so now let's see, we found the median and the 2 quartiles. We still need to find the range. So for range, we want the difference between the smallest and biggest number. So 14 minus 2.5. And that should give us 11.5. Okay, so there's the range. The interquartile range is similar, but it's just from the lower quartile to the upper quartile. So the interquartile range is the upper quartile minus the lower quartile, which is 7 minus 3, which is 4. Now this number tells you how spread apart the middle of the data is. So half of the data is right here. So this tells us that the range from the bottom to the top of this middle portion is 4. So that the nice thing about this is that it ignores any outliers on the low end or on the high end. All right, so now if I want to figure out if there are any outliers, I look at this interquartile range and I multiply it by 1.5. And 1.5 times 4 is 6. So I don't want any outliers would be numbers that are more than 6 units higher or lower than the median, which is 5. So so on the low end, 5 minus 6 would be negative 1, and we don't have anything lower than negative 1. On the high end, 5 plus 6 is 11, and we do have one that's higher than 11. This right here is an outlier. Okay, so that we've answered the question. We found the range, the interquartile range, and any outliers for the set of data. And we will, in the next section, look at box and whisker plots, which actually use the range and the quartiles and the median. So this information, even though it seems like it may not be giving you a whole lot of information right now, other than just, again, how spread out the data is, It will actually be useful for box and whisker plots, which will give us a good visualization of the distribution of the data. But for now, we just want to make sure that we can correctly calculate each of these things. So for the try it yourself problem, we're going to do the same thing. So find the first the median and the quartiles, and then use that to find the range, the interquartile range, and any outliers. So go ahead and pause the video, work through that, and when you're ready to check your answer, press play. Okay, for this one, you should have had a lower quartile of 5, median of 13, and an upper quartile of 17. That gives you a range of 32 and an interquartile range of 12. So 1.5 times 12 would have given you 18. So you're looking for numbers that are more than 18 units away from 13. So 13 minus 18 would have given you -5. There's nothing smaller than -5. 13 plus 18 would give you 31, and there is a number that's bigger than 31. So this is an outlier.